So we'll get started here. 6.2, as it says here, variance, standard deviation, and continuous random variables. So today what we're going to do is, yesterday we talked about a discrete random variable, then we calculated out its mean. It's the average or the expected value. What would we expect to get if we did if we selected one person or one item from our random variable? What's the average amount or the average value that that person would get? What we're going to do today is take a look at its standard deviation. Basically, on average, how much is it varying from the mean? Because if the standard deviation is small, then we know that the outcomes are going to be pretty close to that mean. But if we get a really big standard deviation, well, that tells us that, boy, we can have all sorts of different types of outcomes. Now, calculating out the standard deviation of these random variables is a big calculation. It's the biggest calculation that you will actually do in this course, okay? And it has a simple pattern to it, but sometimes depending on how big your probability distribution is, the calculation can get rather long. So if you take a look here and in your notes, first thing you have to have is your probability distribution. So the first thing you actually have to do, okay, in order to calculate out the variance, the first thing you have to do is calculate out the mean. So you actually have to find the mean first, because the mean is used in the calculation of standard deviation. So if we recall way back to our chapter 1 days, okay, on calculating out standard deviation, okay, we actually would calculate out the variance first. The variance is, again, just the standard deviation being squared. So what we would do is we'd start to take a look at how far away is our result away from the mean. So what happens is you're going to take each of your outcomes that's in your probability distribution function, this x1, x2, x3, it might be 0, 1, 2, 3, or 10, 20, 30, 40, whatever the numbers are, and you're going to subtract it or subtract the mean from it. But because sometimes they might be less than and sometimes they might be greater than, you're going to get some positive and negative values. And if you were to add those up, they'd add up to 0 because you're comparing it to the mean. So what we do is we square them. So each of them have to be squared. Then they have to be weighted according to their probability, because they're not equally distributed amongst the outcomes. So you have to multiply each of those by the weight of their probability. So you have to do a calculation for this one, and then this one, and then this one, and you sum it all up. This is your variance. Okay? Now this is not the standard deviation. To get the standard deviation, all you have to do is take the square root of the variance. So once you calculate out that answer, okay, take the square root of it and it will give you the standard deviation. Now notice the symbol notation. Sigma is standard deviation, but squared, this is variance. So if you see sigma of x squared, that means variance of x. But sigma of x is equal to the standard deviation of x. So knowing what those symbols represent is important. So what we're going to do today to start off is show you how to set these up, calculate them, and interpret what they mean in the context of the problem. So let's take you through the calculation and the setup. So on this excuse me, first example here, so I'll move it up just a little bit more. Sorry, I moved it up way too high. There we go. So it says, okay, let X equal the number of courses at which a randomly selected student at a certain university is registered for. Okay? The probability distribution of X is below. So we're talking anywhere from 1 course all the way up to 7 courses. Wow, 7 courses, that's crazy. Okay? I think the most I ever took at one time was maybe 5. I'm trying to think if I ever took 6. No, I could remember taking 5 though. So it says show, in question A, it says show that the probability distribution is legitimate. What 2 things must be true for it to be legitimate? Okay. They have to add up to 1. So does the sum of the probabilities equal 1? Well, let's find out. What's 0.02 plus 0.03 plus 0.09 plus 0.25 plus 0.40 plus 0.16 plus 0.05? Well, let's see here. 5, 14, 39, 79, 89, 95. Woo, adds up to 1. Check. Are all the probabilities between 0 and 1? Yes. So, everything is good to go. So sometimes you'll be asked to check that, but it's always good just to make sure that, Mr. Bartz didn't screw up writing the problem or everything was done correctly. All right, so now the second part here says compute the mean of the random variable and interpret its value in the context of the problem. So the mean of X. Who remembers how we do this from yesterday? What do I need to do? What am I multiplying? Okay, the X value with the, and I need to do that for all 7 courses here. So this is going to be a fun calculation. So 1 times 0.02 plus 2 times 0.03 plus 3 times 0.09 plus 4 times 0.25 plus 5 times 0.40 plus 6 times 0.16 and 7 times 0.05. So I know some of you are saying, that's a long one to calculate out. I agree with you, it takes a little bit of work. But just wait till we do the variance. Ho, ho, ho. Alright, so I'm going to take out my calculator. Hopefully you have yours. Shoot, I didn't have my calculator on, so this is going to take a little bit longer. I thought I had it still on. Oh no. So some of you might get the answer before me, which will be good. So it's going to load it up. Validate my license. 5, 4, 3, 2, 1. Hey, there we go. Alright, so I'm going to clear, large screen it, even though I'm going to move it way over here and slide this one over so that I can do the calculation and at the same time. So 1 times 0.02. I suppose I could have just typed in 0.02 there. Plus 2 times 0.03. Plus 3 times 0.09. Plus 4 times 0.25. Plus 5 times 0.40. Plus 6 times 0.16. Plus 7 times 0.05. Hopefully I typed those all in correctly. Did you get 4.66?
Yeah.
Whew. So the question is, what does this represent? What does 4.66 mean in this context? Yeah, so and a mean is a average, so we would say the average, yep, you got it, number of courses. So we say the average number of courses a randomly selected student takes at this university is 4.66 courses. Wow. All right, how are we doing so far? I'm okay, you're okay. You guys are also quiet today. All right, now it says compute and interpret the standard deviation of the random variable. So in order to calculate out the standard deviation, you actually have to calculate out the variance first. So I'm going to do the variance. So again, I write the symbol notation. Sigma of x squared. Okay? And again, that represents variance. So again, here we're going to go variance first. Then once I get that answer, just simply square root it. So now, how do I calculate it out? Well, according to the rule, I take each x, subtract it from the mean, square it, and multiply it by its probability. So the first number in my table here was 1 with a probability of 0.02. So how I write this out is 1 minus 4.66 squared times 0.02. That's just the first one. I do it again now for the second one. Now it's 2 minus 4.66 squared times its probability. I'm just going to lower this down just a little bit because I can see the probabilities right here. Okay? Times 0.03 plus 3 minus 4.66 squared times 0.09 plus 4 minus 4.66 squared times 0.25 plus 5 minus 4.66 squared times 0.40 plus 6 minus 4.66 squared times 0.16 plus 7 minus 4.66 squared times 0.05. Wow!
Can you wait like 2 seconds?
I will wait several seconds for you. Okay. I wish there was a faster way on our calculator to do this, but I find that if I were to enter these in lists and have it like do this minus this list and do summing, it will take just as long. So I found that just doing the calculation out, okay, and then plugging this in, okay, to be the challenging part. So now, I'm on.
I would say after you get to answer, you square root it and that's what the standard deviation is.
Yeah, sorry. What?
It's water.
Well, I'm dealing with some bronchitis, so. Yeah, how fun. So, what's that? It will help? Okay, good to know. Anyway, once your question is, once you do this calculation, take the square root and you got the standard deviation. That is absolutely correct. The fun is just typing this long one in. Most of the problems that you'll have in your assignment will be a little bit shorter. This has 7 probabilities. what makes it nicer is when you only have like 6 or 5 or 4 or 3 probabilities, then these calculations shrink. It's when you have like 22 probabilities, you just want to go, oh no. Alright, can I go ahead and start typing it? What I like to do is type it just how I wrote it, except I don't need to put a parentheses around each of the probabilities, but I do need to put a parentheses around the first part. So as I type this in, I'm going 1 minus 4.66, close my parentheses, squared, go ahead and hit the squared key, times 0.02. So then I write the second one. So I go plus, and I do the second one, 2 minus 4.66 squared times 0.03 plus 3 minus 4.66 squared times, what was it, 0.09? Plus, now I do the 4s, which is times 0.25. So parenthesis, 4 minus 4.66 squared times 0.25. Okay. Plus, now I'm going to do the 5, 6, and 7. Okay. Parentheses, 5 minus 4.66, close my parentheses, squared, times 0.4, plus, parentheses, 6 minus 4.66, close my parentheses, squared, times 0.16. Am I still typing this in right? Is anyone watching me? That's your job right now. 7 minus 4.66 quantity squared times, what's the probability? 0.05? 0.05. Let's hit enter here. Ooh, 1.444. Nice. Is that our standard deviation?
Yes, sir. No, it's a.
That's our actual, I have 4 4s. That's our variance. So right now my variance is 1.4444, but I want the standard deviation, so square root both sides. So what I can do is now on my calculator go square root of my answer, hit enter, and I have my standard deviation. So you can decide how many decimal places you want to go out. How many do you want to go out here?
2.
Okay, so we can say 1.20. Oh, sorry. Yeah, I just wish I wasn't coughing so much. So the question is, what does this value mean? Okay. So we're just basically saying, on average, the number of courses taken by a randomly selected student at this university will vary from the mean by 1.20 courses. So we can think about it like this. All right, our mean was the average randomly selected student is going to take 4.66 courses, but that will vary on average by 1.2 courses. Kyle,
Could you scroll up?
I can scroll up, sure.
Pages for a minute, please.
Oh, I'm sorry, was I going too fast?
No, to these ones.
Oh,
Sorry.
to.
Yeah.
Okay.
Thank you.
So yep, make sure that you know that this symbol with the squared is variance, and this symbol here is for standard deviation. Because later on in our lessons, we'll talk about adding and subtracting random variables. What happens to the variance? What happens if instead of selecting one student, what happens if I select two students at random? What happens to the mean and standard deviation? Alright, let's go then to our next page. Are we okay, or does anyone need the bottom? Sure. As you're waiting for me to go to the next page, why don't you flip to the next page and start working on calculating out the mean and the standard deviation of the second problem. I believe it's talking about eggs. So why don't I do this? I'll flip to the next one. I'm going to read the problem, then I'm just going to give you a little bit of time to work on it first. So it says, let y equal the number of broken eggs in a randomly selected carton of 1 dozen store brand eggs at a certain market. The probability distribution of x is shown below. So 0, 1, 2, 3, or 4. Is this a legit, even though they don't ask you, do the probabilities add up to a 1? Yeah, 65, 85, 95, 99, 100, good. I always check that, just to make sure. So I'm going to give you a 2-minute head start. I want you to. Alright, I'm going to write up the mean. Many of you I've checked with, but I'll show my work here so that you can actually see. So the mean of y equals 0 times 0.65 plus 1 times 0.2 plus 2 times 0.1 plus 3 times 0.04 plus 4 times 0.01, and the number is 0.56. So what does that mean? The number of broken eggs oh, I apologize, it's not the number, it's the average. Oh, Mr. Bartz, I'm going to start that over. It's the average number. The average number of broken eggs found in a randomly selected carton of eggs at a certain market is 0.56 eggs. So a little bit more than a half an egg. I know you're probably saying right now, well, you can't have a half an egg broken in a carton. I agree with you. But this is the average, which is actually pretty good if you're thinking about a grocery store and eggs. It's less than 1. If you think about how when you go grocery shopping, how often do you get home and at least one of the eggs in the carton is broken? Right? Happens from time to time. Did you forget to do the squares?
Bart, did you ever open a carton and buy them?
All the time.
So how do you come up with it's broken?
It gets jostled in the car. Some way, shape, or form, you know. Something happens. Or it's broken, but it was broken on the bottom, so you didn't see it.
Yeah, you don't want to touch that.
Yeah, you don't like, I don't open up the carton and pick up every single egg. I mean, it doesn't bother me too much. I mean, usually a dozen eggs these days costs about $2, so one egg, you know, I don't feel put out when I have one cracked egg. Unless I'm making something that requires exactly 12 eggs, which is almost never, and now you got 11. So, alright. Excuse me. So some of you are already ahead of me on the standard deviation. So in order to do standard deviation, first you do the variance. So variance in this case, notice how I write the squared with it. Standard deviation squared. So I'm going to go each outcome, so 0 minus 0.56 squared times 0.56, or times its probability, which I think was 0.65. I need to lower it just a little bit so I can see those probabilities. Plus 1 minus 0.56 squared times 0.20 plus 2 minus 0.56 squared times 0.10 plus 3 minus 0.56 squared times 0.04. See if I can squeeze it. 4 minus 0.56 squared times 0.01. Oh, I knew that was going to happen. Times 0.01 here. Trying to squeeze it there. So, I'll let you guys see what you get for your calculations. I'll peek on my notes here to see if you guys are getting the same value. So I'll check the first one. Beautiful. Yep.
Mr. Burns, I have a question.
Yeah, I'll be right there. I'm just going to check a couple. Yeah, beautiful. We are over 3 for 3. I love it.
Is there any way I can go back to when I typed to add something to get
Yes.
the answer?
Second enter, second enter, second enter. There we go.
Oh,
And now you can go back and edit.
then it's squared after that.
On this one, you forgot the square.
Yeah.
So what I can do is go second delete, which is an insert,
Okay.
and it'll let me insert it. And I don't need to do another parentheses. Perfect. Alright, I've checked about 5 of you right now, and this is what, it was 0.8064. So then what I have to do is square root, square root. So the standard deviation is 0.8, was it 898? Or if you said 0.90, some of you might have. I'll double check that. Yes. So, so what does that value actually represent? Yeah. The standard deviation, which means the average number of broken eggs from, or I should say found, sorry, I'll be consistent with the problem above, from, or found in a randomly selected carton of eggs, or eggs, I forgot the S on this one, at a certain market will vary from the mean by 0.898 eggs. So almost 1 egg. And that can happen. I know some people will be like, well, that's kind of weird. Your standard deviation is bigger than your mean. Oh yeah, That can happen. This tells you that you actually have a little more variability than you would expect. Alright, how are we doing on the calculations? Not too bad? Okay. Alright, one more concept that we're going to talk about here today, and then after we do some examples of it, we'll be done and I'll give you some work time here. And that is the concept of a continuous random variable. Okay? What happens in a continuous random variable? Unlike a discrete random variable, the continuous random variable goes on and on and on forever. Sometimes like some of my lessons. They just keep going. Okay? But what we're thinking about in a continuous random variable is there's an infinite amount of possibilities. However, it might still be in a finite space. But all the possibilities in between two numbers are possible. So when you're calculating out a probability in a continuous random variable, you're going to take a look at an interval of numbers. And specifically, you'll take a look at an area. Okay? So for instance, if we go back to our days back in chapter 2 when we talked about density curves. Okay? A density curve will give you basically the pattern of what your distribution will look like. But one of the things here is if I have a density curve of some kind, so if it's like this, okay, I know that my area underneath the density curve will equal 1. One of the most common density curves that we talk about is the normal curve. Okay? And if you remember, back in chapter 2, if something was normally distributed, we could calculate out the probability of something by looking at the interval going from one score to a second score. We calculate out z-scores and calculate out and use our table A or use our calculator to find it out. We can do the same thing if our density curve are nice shapes. Like for instance, this one here, if you look at it on the paper or on your notes, is simply a square. Notice how the base has a length of 1 and the height has a length of 1. That's done on purpose because 1 times 1 gives you the area of the square to be 1. So if you want to find the area or find a continuous probability, you have to find an interval. Because there is technically an infinite amount of numbers between 0 and 1. You could have 0.1, 0.01, 0.001, 0.00001. I can keep on doing that forever. Okay? So one of the things that's true in a continuous probability model is that each individual outcome is actually equal to 0. However, you can find a set probability by calculating out its interval. Alright, so again, the most common one here, we already talked about this, is the normal curve. So we'll actually see a problem today and we're going to revisit our stuff from chapter 2. So I know some of you are saying, well, should I keep my notes? And here's where chapter 2 comes back. Alright, so let's flip to our last page of notes and take a look at some examples here. Okay? So in number 1 here it says, suppose we have a continuous random variable with a uniform distribution where x goes from 0 to 20. Okay? In question 8 it says, draw a picture of the density curve representing our continuous random variable. What is the height of the curve? So, first of all, it says our x values goes from 0 all the way to 20. So any outcome from the number 0 to 20 is possible. The nice thing about this is it says it's uniform. When we talk about a distribution being uniform, we're talking about it being the same. So what it means is the probability of each of those outcomes are exactly the same. We're going to go straight across here with the same height. So the question becomes, what in the world is the height of our curve? How in the world are we going to find that? Here's my first question for you to help you. Okay? Oh, good. Area has to equal 1. What's the shape? Not a square, but a rectangle. So how do you find the area of a rectangle? So base times height here has to equal 1. Yeah. So what's the base? 20. Because you're going from 0 to 20, so it has a length of 20 units. Height is what we're looking for. So if you divide by 20, 1/20th, or it has a height of 0.05. So now, what we can now do is answer the following questions here. In part B, it says, what's the probability that x is less than 15? So a lot of times what I do to answer these questions is draw a little sketch of it. I know it goes from 0 to 20 now. I know the height is 0.05. Here's my density curve. I'm looking for values that are at 15, or really less than 15. So I'm going in this direction. So the question becomes, what's that area? So I use this formula to calculate it out. What's the length of my base? What's my height? 0.05. 15 times 0.05? 0.75. You got the first one. So I continue to do this same process. Greater than 0.8, or I'm sorry, not 0.8, but 8. So this is 0.05. Here's 20. Here's 0. So I'm looking at 8 or greater, or actually greater than 8. So all of those. So what's the length of my base there?
12
So 12 times 0.05
is 0.6.
is 0.6. First I thought I heard 6, I'm like going, wait a second, we can't have a probability of 6. Alright, next one. Between 6 and 12. So 0, 20, 0.05. Now we're going from 6 out to 12. I'm looking at that area right there. So the base is 6, the height is 0.05, you get 0.3. It can be 12, yes, but whether it's 12 or not 12 will not change the probability, because the probability of a single outcome is 0. So you're still just doing this area right here in between. This base has a base of 6, and you're timesing it by the height 0.05. So that kind of is the sneaky part of this one, but if you visualize it, it will help you. Okay, so 0, 20, 0.05. I'm looking for x equaling 10. What's the base? It has a length of 1? It doesn't have a length, does it? 0. Times the height of 0.05 is 0. That's why it's 0. It doesn't have actually a length for the base. So any exact number, okay, has a probability of 0. Can't calculate it out. All right. So let's give you one more example of a continuous random variable. Last one. Number 2 says the weights of 3-year-old females closely follows a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. So now that I know what the variable is, off to the side here, I'm going to say, well, the mean of X was 30.7. The standard deviation of X they gave me as 3.6 pounds. Here's the other piece of information that's very important. Normal distribution. So I know that something's normally distributed. So in part A, it says find the probability that a randomly selected 3-year-old female weighs at least 30 pounds. So if I'm writing the symbol notation of this, I'm saying, well, what's the probability that X is greater than 30? So it helps to visualize what's going on here. So I'm thinking about this saying, all right, I have a normal curve where the mean is at 30.7 pounds. If I were to go one standard deviation and subtract 3.6, I would be at 27.1. So what I'm looking for is, what's the probability that I choose a random 3-year-old that weighs 30 pounds or more? So I'm trying to calculate out that specific area. So with normal curves, what would we actually use? Or what would we have to calculate out first to get this value? Do you remember what type of score we need to figure out? Yeah, z-score. So how do we calculate out z-scores again? What comes first? Okay. Remember, a z-score is how many standard deviations is your score away from the mean. Okay, so it's going to be something divided by the standard deviation. Is it your score minus the mean, or is it the mean minus your score? It's going to be your score minus the mean. And here's how I help myself remember. If it's to the left, my z-score is a negative score because I'm below the mean. Okay? So since this value is less, the smaller minus the bigger would cause a negative number. That's how one of the ways I help myself remember is it which one is it. So you're always taking your score minus the mean divided by the standard deviation. So in this case, z equals your score 30 minus 30.7 divided by the standard deviation of 3.6. So, pull out my calculator real quick. 30 minus 30.7. Some of you probably knew that that was negative 0.7. Divided by 3.6, negative 0.194. Remember, with z-scores, we like to go to 2 decimal places. So this is the probability that z is greater than negative 0.19. So we can use table A, but many of you like to use the calculator, don't you? So do you remember what function we use in the calculator to get this value? Ooh. Okay. Well, what type of curve do I have? What type of distribution? So normal, you got it. Cumulative distribution function, yep, CDF. Now I have to put 2 numbers in here. Lower bound, upper bound. So what's my lower bound here? What's my lower bound z-score? This negative 0.19, what we just found. What's my upper bound? How far does it go?
Oh, is it like 99?
Yeah, you do a bunch of 9s to represent positive infinity. So 99 will probably be enough. So now on my calculator, second vars, number 2. So negative 0.19 to 999, or however many 9s you want. It's going to give you your probability, 0.5753. So we can say the probability that a randomly selected 3-year-old weighs more than 30 pounds is with 0.5355 5753. Ooh, I feel that dryness coming. Oh, there. All right, one last problem. Move this up. B says find the probability that a randomly selected 3-year-old female weighs between 27 and 29. Yep, you're right, Carter. Same thing, except just different x values. So I want to know between 27 and 29. So what's nice about the picture up top, again, here's that 30.7. I can think about it like this. 27.1, so it's just a tad bit lower than 1 standard deviation to 29. So it's going to be this sliver of the normal curve. So I have to calculate out not 1, but 2 z-scores. So I'm going to go 27 minus my mean 30.7 divided by 3.6. And then I'm going to go 29 minus 30.7 divided by 3.6. So we'll do a quick calculation of both of those. 27 minus 30.7 divided by 3.6. So negative 1.03. Do the second one. 29 minus 30.7 divided by 3. Whoops, I have to hit enter there. 29 minus 30.7. I have to hit enter since I didn't put it in parentheses. Divided by 3.6. Negative 0.47. So really I'm looking at what's the probability that my z-score is between negative 1.03, whoops, and negative 0.47. I wrote 4.2 for some reason. So I think it ended in the 2 repeating. So, normal CDF. What's nice about this one, this negative 1.03 is the lower bound. Negative 0.47 is the upper bound. So second vars, normal CDF, negative 1.03 to negative 0.47. 0.1677 if I round. So then I can say the probability that a randomly selected 3-year-old weighs between 27 and 29 pounds is 0.1667.